This video demonstrates the orthogonality property that exists among OFDM subcarriers, which is a property that allows the data that is modulated into each of these subcarriers to be fully independent and immune from interference coming from the other subcarriers. The model we'll use to prove this orthogonality property is based on real passband signals. That is, the actual signals that would be used in a passband OFDM system, which will avoid the complications derived from using the low-pass equivalent of the system, which calls for complex signals. In this case, we'll use only real signals. Also, to simplify the mathematical expressions involved in this model, we're going to assume binary PSK or BPSK modulation into each of the subcarriers. This is, of course, an important departure from actual OFDM systems, which use more complex modulation schemes, such as QPSK and QAM. However, this model can be easily extended to these types of modulation by just adding a phase term to the modulated signal and an IQ two-branch detector instead of a single branch detector, which we will use in this model. Our OFDM signal model will assume a total of n plus 1 subcarriers, where n is going to be assumed even. In this case, we have a subcarrier aligned with the carrier frequency omega c. That is typically not the case, but in this case, it doesn't hurt to have just an additional subcarrier at that frequency. The subcarrier spacing we call delta omega, and that is given by 2 pi delta f, and where delta f is just the inverse of the symbol time of the OFDM symbol time. The mathematical model for our OFDM signal follows this expression, where you can see the summation of all the subcarrier components going from I equal to negative n over 2 to plus n over 2 to cover all the subcarriers here shown in the spectrum. And each of those terms is modulated in BPSK, where the modulation is given by this constant b sub I, that is the bit that is modulated into the ith branch, and the corresponding subcarrier, which is at a frequency omega c plus I multiplied by the frequency separation. The orthogonality property will be shown for the case of detecting one of these particular subcarriers, the kth subcarrier, which is at omega c plus k delta omega. So we're going to show that when demodulating this particular subcarrier, we're going to see no interference from the other subcarriers. And that, of course, is valid for any value of k between negative n over 2 and positive n over 2. Our detector model consists of two sections. In the first section, we have a BPSK demodulator, which is a simple, coherent down converter, which will take the signal from the carrier frequency omega c and demodulate it to baseband to deliver a baseband signal z of t. And this demodulator is tuned specifically for the case subcarrier, so that the local carrier for this demodulator is at omega c plus k delta omega, and that is our selected subcarrier. The second part of the model is the BPSK match filter detector for rectangular pulses, which is the pulse shape that we're using in this OFDM model, which is the typical pulse for OFDM signal, just a rectangular pulse. And that match filter detector consists of an integrator between going from 0 to TS, that is a symbol time, and then followed by a sampler at t equal ts, and then followed by a zero threshold detector, which will determine whether the received bit for the kth branch is either a 0 or a 1. So let's look at the expression for the signal y of t that's coming out of this multiplier, this mixer here, and that will be the product of the OFDM signal. You can see the OFDM signal here, multiplied by the local carrier for the kth subcarrier, which you can see there. And that can be rewritten into this form. You can see that this is a term that has, again, n plus 1 components, a summation of n plus 1 components, which can be rewritten by using this trigonometric expression, cosine A multiplied by cosine B, equal to 1/2 cosine of the sum of the arguments plus the 1/2 cosine of the difference of the arguments of the cosine. And the result of that will be this trigonometric identity here, where you still have n plus 1 terms in this summation, but now you have the sum instead of the product of two cosine functions. So if you look at this summation here, you can see that this y of t signal, which is going to go through a low-pass filter depicted here, will be will see one of its components removed. This is the component that is sitting at 2 omega c. This is a high frequency component. It will be rejected by the filter. And therefore, after filtering, we will still see a composite OFDM signal consisting of n plus 1 terms, but now they only contain low frequency terms such as the one shown here. The integrator is operating between 0 and Ts, so we're going to have this signal integrated from t equals 0 to Ts, and the next step is to swap the order of the integral and the summation, and then replace delta omega by 2 pi over Ts to get this more simplified expression that now can be rewritten in the following way. So here you see a summation with n plus 1 terms. We're going to separate the term at I equal k, that is the term corresponding to I equal k will be taken off the summation and will become this term here, that is the desired component that we're trying to demodulate. And then this summation now contains only n terms, each of them consisting of the product of the bit for the corresponding branch, and then this integral between 0 and Ts of the cosine at the frequency given by I minus k 2 pi divided Ts. So we're going to go ahead and solve these two integrals. This integral here will give you t multiplied by bk divided 2, and then again we need to evaluate between 0 and Ts, and then the cosine here, which can be integrated easily to give a sine function. Again, this needs to be evaluated between 0 and Ts. When we do those evaluations, the first thing we'll notice is that this term here is sine at I minus k multiplied by 2 pi. Now, I minus k is an integer number, so we're going to have the sine of an integer multiple of 2 pi, which is, of course, 0. Same thing can be said about sine of 0. So in the end, this whole summation consisting of all the terms of all the subcarriers except the kth subcarrier becomes 0. And we are left only with this term, which is the desired term at the kth subcarrier. So when we sample this signal at t equal Ts, we'll see that the result of the sample will be Ts, that's a constant, multiplied by bk, that's the bit on the kth branch, divided by 2, or in other words, plus minus Ts over 2. That is the information bit for the kth subcarrier, which is free from any interference from any of the other subcarriers, which shows the orthogonality property that we're trying to prove.